week we're going to study about boundary value problems. So far we've considered equations which evolved in time, and they are classified as initial value problems because the initial conditions are known, and then the system state and things such as plotting the state in the phase diagram, they are the evolution of the parameters in accordance to how they are governed, and they are initial value problems. But in a different category of problems, we can have a domain such as a string, and then you can impose certain conditions. For example, you can have a displacement of the string like this, and this end of the string is left free, things like that. So things which we are familiar with, things pertaining to vibrations and all these things, or displacements, and they all fall within the purview of boundary value problems. So without any delay, let us look at a particular very simple boundary value problem. D2f dx2 is equal to f. So it's a linear ODE, and we have to define over what domain is this particular equation valid. So let us take it over the domain 0 to 2, and at x equal to 0, let's say f of x is equal to, you could directly write the first boundary condition as f of 0 equal to say 1. Second condition could be f prime of 2 equal to 0. So this in a solid mechanics viewpoint, this would be a prescribed displacement, and this would be a free or unconstrained um, member. So something which maintains a slope, but it does not define what the displacement will be. Okay, so it has to just maintain a slope. It could go from something like this also. Not this much. It could go something like this. All it has to do is maintain this displacement. There is no prescription for it, and maybe we have to find that out as a part of the solution. Who knows? So these are the two conditions, and this condition is known as the Dirichlet condition, and this particular condition is known as the Neumann boundary condition. So here the value of the function is specified at the endpoint, one of the endpoints, and over here the derivative is specified. And so this is how you distinguish between a Dirichlet and a Neumann. Alternately, you could have the situation where you have a mixture of both, that is something like f prime at 2 plus twice f of 2 equal to a or something. So it's a mixture of the first derivative and the specified value of the function, and this kind of boundary condition is known as the Robin boundary condition. Okay, so how do we go about approaching this problem? Well, first thing we could do is obtain the analytical solution. So what is the solution for this? So f, so it's a easy equation, is a cos h x plus b sin h x, and that's the straightforward solution. You could write the solution for this as a to the power x plus b to the power minus x. That is a linear combination of e to the power x and e to the power minus x, where the constants a and b are determined using the boundary condition. So in fact, let us use this hyperbolic form. So we have f equal to a cos h of x plus b sin h of x using the first boundary condition f0 equal to 1. So 1, so when once you substitute x equal to 0, this term will become 1, so this will be a, and this particular term will become 0 because sin h of 0 is 0. So a becomes equal to 1. And similarly, using the Neumann boundary condition, so what do we have? 0 equal to a sin h x at x equal to 2 plus b cos h x at x equal to 2. This becomes a sin h 2 plus b cos h 2, and a is already equal to 1, and this implies b is equal to minus sin h 2 upon cos h 2. So combining this, so this is the solution, yeah, where a is this and b is minus sin h 2 upon cos h 2. So we could write down the expression by substituting all this over here, but because we're going to plot it in Python anyway, or Octave as you like, so we're not going to bother much about that. So let us go and create a new file. So let me copy this bit of code. All right, so let me then create a linspace between 0 and 2. And let me call it xc. This is for x exact, and y exact is a times np dot cos h xe plus b times np dot sin h xe. We can send this to the next line because we need to define the constants a and b. So a is 1 while b is equal to minus np dot sin h of 2 divided by np dot cos h of 2. Well, alternately you could have written it as minus np dot tan h of 2. But anyway, this is fine. So with this, let us do a plot. So this is how the exact solution looks like, and the value of the function at the other endpoint, that is x equal to 2, appears to be something which is near to 0.3 but less than 0.3. So this is what we have from the exact side, but now we are interested to solve this numerically. So how do we go about solving it numerically? Let's see. So the first thing that we do, the very first thing that we go about doing is to discretize the domain into a bunch of points. So this is x equal to 0 and this is x equal to 2. This is going to be, so we make a linspace out of this. So this will be 0, 1, 2, all the way to n minus 1. So if we have a linspace which has n elements, so let us do that and see. So let us keep this code over here and let us write this here. So x equal to np dot linspace 0 to 2, and let's say we take 20 points. And yeah, so let us print x just for good measure. So this is how x looks like. The 0th point is 0 and the last point, so 0 will be 0, whereas 19 will be 2. So it's going all the way from 0 to n minus 1. Alright, so now our task is to discretize this particular equation over on this grid. So we have what, d2f dx2 equal to f. So how do we discretize a function at a point? So I must write the function in terms of the neighboring points. So the very easy way of doing it is writing a central difference approximation. All right. So I mean, I whether or not it is clear how to do this, I'll just give you a gist of how it is done. So we have f of x equal to f of x naught plus df dx at x naught times delta x plus d2f dx2 at x naught times delta x square by 2 factorial and so on. So now f of x minus f of x naught divided by delta x gives us a good estimate of what df dx at x naught is going to be. But we have neglected the other terms, but the magnitude of the other terms, so I've divided everything by delta x. So this will be plus order delta x, meaning whatever I'm neglecting is going to be proportional to the delta x that I have over the grid. If delta x is small, then this approximation is also good. If delta x is large, this approximation is not going to be good. So how do you go about finding the central difference approximation? Well, you have on one hand the approximation for f of x near x naught, and similarly you can write an approximation of f. So what we have, this is x naught, this is well, so I just write an approximation for f of minus x, that is the point on the other side. So f of minus x is going to be f of x naught minus df dx x naught delta x plus d2f dx2 delta x square by 2 factorial and so on. So as you can imagine, if I add these two equations, the odd terms will cancel out because delta x cube term will be there and here it will be minus delta x cube. So all these odd terms will cancel out. So finally we have f of x plus f of minus x is equal to twice f of x naught plus d2f dx2 at x naught times delta x square plus order delta x to the power 4 and so on. And so this gives us a good measure of the second derivative as f of x plus or rather minus 2f of x naught plus f of minus x divided by delta x square. And so the error will now be order delta x square because I have divided everything by delta x square. So this also gets divided by delta x square. So such an approximation is said to be second order accurate because as delta x becomes small by say a factor of half, the error is expected to reduce by a factor of 1/4, which is in stark contrast to the forward difference approximation for a single derivative. Well, I've rubbed that now. But similarly, I could, so what we had earlier, df dx at x naught, it was simply fx minus f of x naught by delta x. And now I can choose whatever x and minus x is to be a point coinciding with the neighboring grid. So now x becomes x1 and minus x becomes x minus 1 because f of this minus x is simply the minus 1th node and this x will become the first node if this node is the 0th node. So this approximation was first order accurate, but you can actually evaluate a second order accurate derivative, and the way to do it is gonna be f of I plus 1. So if I call this df dx at xi, it's going to be f at xi plus 1 minus f of xi minus 1 by 2 delta x. Essentially, it is saying that if this is a function, if this is one point I, so if I want to approximate the slope at this point, which is something like this, I can discretize the the grid over which it is defined. So this is I, this is I plus 1, this is I minus 1. So this point is f of xi minus 1. This point is f of xi plus 1. So I can approximate it by taking a difference between these 2 points. That is the central difference. I can approximate it between these 2 points. This is the finite, the forward difference. I can in fact approximate it using these 2 points as well. That is the backward difference. So depending on the scheme that you use, one will arrive at an approximation to that particular derivative, which will have some order of accuracy. And as to what that accuracy will be is a matter of what your choice is. Alright, so let's get rolling with this. So yeah, so d2f dx2 let's is equal to f. So I can do a finite difference approximation at the ith node. So what this will be fi minus 1 minus 2fi plus fi plus 1 divided by delta x square is going to be equal to fi. So obviously the left hand side is order delta x square accurate. Now let me collect the terms containing, let me segregate the terms fi minus 1, fi and fi plus 1. So I have fi minus 1. Okay, so fi minus 1 is obviously referring to f at xi minus 1. Okay, so this is just a small shorthand for writing. Plus fi, this will be minus 2 minus delta x square plus fi plus 1. This is equal to 0. Oh, you have many nodes and here is 0. And you have many nodes and here you have n minus 1. Okay, here you have n minus 1. So now this particular discretization, let me call it as A. So this is valid for the interior nodes, because we must treat the boundary conditions a bit differently, in the sense that I know that f of 0 is equal to 1 and df dx at x equal to 2 is going to be 0. Now while we're at it, let's have sort of discretization for this fellow as well. So this is quite trivial. This is simply going to be f0 is going to be 1. And this is going to be, so let me take a backward difference at the final node. So backward difference at the final node will involve n minus 1 and n minus 2. Fine. So this will be f at n minus 1 minus f at n minus 2 by delta x is going to be 0. Alright, so this is for node number 0. This is for node number n minus 1. And what about the inner nodes? Let me substitute I equal to 1 over here. So what do I have? I have f0 plus f1. So let me call this as alpha, because it's not going to change over the equations, because we will have a regular grid, meaning delta x is not changing across various locations on the grid. So that kind of a grid is called as a uniform grid or a regular grid, no problem. So it's going to be f1 times alpha plus f2 equal to 0. Now what I can do is I can write it for I equal to 2, 3 and so on. So this is for I equal to 1, I equal to 2, I will have f1 plus f2 alpha plus f3 equal to 0 and so on. For I equal to 0, obviously I have f0 equal to 1, and for f for I equal to n minus 1, I have fn minus 1 minus fn minus 2 equal to 0, because delta x can go on the right hand side and it will be obviously 0. Now what I can do is write down these equations. So for for n equations, I have n unknowns. The n unknowns are f0, f1, f2 all the way to fn minus 1. And how many equations do we have? We do have n equations starting from I equal to 0 to I equal to n minus 1. So it's a set of linear algebraic equations. So we've converted the ordinary differential equation into a set of linear equations. Alright. So if I can go ahead and write this in a matrix form, how will this particular set of equations look? So over here I have f0, f1, f2 all the way to fn minus 1. So fn minus 2 comes on top. And this will be equal to something. So this kind of equation will always come out in the form ax equal to b, where A is like the mass matrix. I mean, it borrows its nomenclature from solid mechanics or structural mechanics. It's the stiffness matrix. Okay, so B is the right hand side. Okay, let's not allude to that nomenclature now. So we simply obtain this set of equations x equal to b. I've forgotten most of structural mechanics, but yeah, you do get an equation of this particular form over there as well. All right, so this is a matrix, this is a vector, this is a vector. So let us populate those vectors. So what do we have? So f naught. So for the first node, f naught equal to 1. So this will be 1, 0, 0, 0, 0, 0 equal to 1. So this is 1 times f1 equal to 1. Over here we have 1, alpha, 1, then all zeros. This is going to be equal to 0. Over here we have, so there is no f0 over here. So this becomes 0, is alpha, this is 1, is alpha, 1, and everything else is going to be 0. Again, 1, sorry, this is 0, 1, alpha, 1, 0. So this continues on. So apart from the first row and the last row, this keeps on continuing. This tridiagonal set keeps on continuing up until the last node, upon which we have a backward difference to take care of. Alright, so the backward difference in this case is quite simple. It simply implies fn minus 1 equal to fn minus 2. So this is minus 1 over here, and this is going to be 1, and this is equal to 0. Why is it minus 1? So all these are going to be 0. This is minus 1 times fn minus 2 plus, so basically this particular term, plus 1 times fn minus 1 is equal to 0. Alright, great. So now our task is to construct the matrix A and the vector B, and then solve for x. Okay, so solution x, I mean over here I'm writing it as x, but it will be really f. Great, so let's go over here. In fact, yeah, so we do have an expression for x. So now what will be the size of the matrix A? So A has to be a square matrix having the same size as x. So it will be np dot zeros, and the size will be, so let me soft code it as n, where n will be the number of points. So n equal to 20. All right, great. So A has been initialized to zeros. Now what will be B? So B will be np dot zeros. So it's n rows and one column. Right. So A has been initialized, B has been initialized. Now it is a matter of constructing the appropriate structure for A. So what we could do is run a loop from I equal to 0 to n minus 1, and based on this particular logic we can assign all the different members of the matrix. So we're not going to do it like that, but I'm just going to outline how to do it in case you're doing it in C or something where vectorization is not possible. This is how you would do it for I equal to 1, for I in 1 in p dot a range 0 comma n. So a, so what do we have? So if I equal to 0, then you will say a 0 comma 0 equal to 1, else I equal to n minus 1, or rather, yeah, equal to n minus 1. Then what will we do? We will say a n minus 1 comma n minus 2 equal to minus 1, a n minus 1 comma n minus 1 equal to minus 1, rather 1. So these two if else statements take care of the boundary conditions, if rather the boundary nodes. If they are not the boundary nodes, then we continue as normal, else a n, or rather a I comma I, well, I could have written this in terms of I as well, I minus 1. I think it is better to write it in terms of I, because it's already doing the check whether I is equal to n minus 1. So I don't need to write it in terms of n minus 1. I can simply write it in terms of I. Yeah, I think that's much better. So ai comma I will be equal to alpha a, oops, I comma I minus 1 is going to be 1, a I comma I plus 1 is also going to be 1. So essentially it's assigning the three values, and you can figure it out whether how this is going to work. So let me define what alpha is. So alpha we had defined as minus 2 minus delta x square. So minus 2 times minus dx square. So what is going dx gonna be? Dx is gonna be x1 minus x0. It's simply the difference between two nodes. Alright. So let me run this and let me show you how a looks like. In fact, let me reduce the number to something manageable like 5. Alright, so this is how a looks like. So look, it's 1 over here and all zeros, and 1 minus 2.251, 1 minus 2.251, and the boundary nodes are different, but everything else is like a tridiagonal matrix. And actually, boundary value problems where you're discretizing with the nearest neighbor, it does resemble a tridiagonal matrix. Alright, okay, so yeah, this is what you can do to construct A, but it's actually looping over all the elements and doing it. We can alternately take a great shortcut. Let me comment. I cannot comment over here. Okay. In fact, let me split cells and keep it for later. So what we will do is we will use the np.diag function. So what is the np.diag function? So let me show you. So let some small a be 1, 2, 3. Right. So a equal to np.diag a comma 0. So now let me show what a is. So it will take a vector and it will push all the vector elements to the diagonal elements. So I have to pass a vector which is having the same size as the length of the square matrix. Alright, so over here it is 3 and so on. So this gives us an idea. So because all of them are going to be alpha except the 0th node and the n minus 1th node, I can handle them easily. Okay, so let me write this. So diagonal vector is gonna be alpha times np dot ones. The size is gonna be n rows, and it's just a vector. dv1 is the offset. Okay, so dv1 is the offset, meaning if b is equal to 5 6 and I write b equal to np dot diag b comma 1, then let me print p. It's gonna take the vectors and it is going to put the vectors in the shifted location to the diagonal. The shift is specified by this. So over it is inserting b, the elements of b, into the matrix capital B and having a shift of 1. So obviously it has to have one less element. The more you shift, the lesser elements you should have. Great, that gives us a different idea. So this is simply going to be np dot ones n minus 1 comma. So yeah, that's it. So now A will be np dot diag of dv plus np dot diag of dv1 comma 1 plus np dot diag of dv1 comma minus 1, where I've used the fact that the upper shifted diagonal and the lower shifted diagonal have the same value to be inserted. Okay, so having done this, let us print what A is. Let me reduce this to 5. So great, we have the tridiagonal matrix as we want. Now I will unset the boundary nodes to be zeros. So A 0 comma all is going to be 0. A n minus 1 comma all is also going to be 0. Let me print and show that we have indeed unset the 0 and the last node. Great. So now we can simply incorporate the boundary condition. So a 0 comma 0 is going to be 1 and the other boundary condition is going to be a n minus 2 comma n minus 1 is going to be minus 1. A n minus 1 comma n, or we don't need to write n minus 1. I'm just being silly over here because we can simply write a minus 1 comma minus 2 is equal to minus 1 and a minus 1 comma minus 1 equal to 1. Man, we've seen this in the very beginning that minus 1 is simply same as n minus 1. Let me in fact print a and convince you. So a00 has been set to 1, a minus 1 has been set to minus 1 and a minus 1 has been set to 1. So now I must also set the B matrix. So B is gonna be, so B 0 is simply going to be 1. That's it. So now we do have the system of equations Ax equal to B, and it's just a matter of solving it. So how do you solve it? I mean, because it's a very trivial case, we take an inverse of A and multiply it. So A inverse A times F equal to A inverse B, and but A inverse A is going to be the identity matrix. So identity matrix times the F vector F is gonna be A inverse times B, and identity matrix times a vector F is gonna be the same as F. So the solution F is going to be A inverse times B. So in fact, let us do it. I mean, it's not the most efficient way of doing it, no sir, but let's do it regardless. So F is gonna be np dot in A, and now we have to do a matrix multiplication. So np dot A times B. There appears to be an error. np dot in So the function inv actually lies inside the linalg submodule. Yeah. So now that we've done this, we can plot it. So plt.plot x comma f. Well, let us try to superpose this with the earlier solution. What was it? Xe and ye. So let me give this a label of approximate or numeric. plt.plot xe ye level equal to exact plt.legend plt.x level x plt.y level this is gonna be f of x. So there appears to be some error. I mean, not some error, but it is exact at the end. But here there is a great deal of error. In fact, one reason could be the very ridiculously low number of grid points. So let me take 50 grid points. Maybe it makes things better. It makes things much better. The numeric and the exact solution does appear to match, but at the end point, there is still something. It's not really matching exactly. Well, maybe if I make it 100 points, it's much better. But well, does it not match as good as the other points? So over here, for example, you can hardly discern that there's some error. But why is this? I mean, let us go back to our working. So the backward difference, this has a truncation error of delta x, of order delta x. Whereas the central differencing that we have used for the interior nodes, it is order delta x square. The truncation order is order delta x square. So we must now come up with an approximation of the boundary condition at the end node, at n minus 1th node, which is order delta x square. And the way to do it is again a central difference scheme. So you have the n minus 1th node, you have the n minus 2th node. Now we have to imagine a ghost node, say the nth node. So this is actually not a part of the domain, it's a extended ghost node that you sort of have in order to do something with it. So now the boundary condition was df dx at n minus 1, or the n minus 1th node, is equal to 0. So f of n minus f of n minus 2 is equal to, divided by delta x, is equal to 0. But because it's using the nth node and n minus 2nd node, it's order delta x square accurate. Alright, the truncation order is of order delta x square. But what do I gain with this? I now have introduced an extra node. So I can write down the equation that I had for the interior nodes for the boundary node as well. So now I can have f n minus 2 minus 2 f n minus 1, or rather plus alpha f n minus 1 plus f n equal to 0. So I can do this. I can use the equation that I had formulated in the interior, because I have extended the domain by one ghost node. So this sort of becomes the interior. This is the ghost node. Very spooky. So now I have an equation in terms of fn, but from this equation I have what? Fn equal to fn minus 2. So substituting this over here, I will have twice fn plus alpha fn minus 1 equal to 0. And now this is the last equation that I should modify everything to. Alright, so let me make a copy of this, or in fact let me change it to A1, and I'll make the other thing as A2, so that we can plot everything in one. So everything is same for A1 and A2 up until the last point. In fact, we could have used np.copy, but anyway, uh, we've done it the hard way. No problem. We could have used np.copy. That is, make a copy of A1 and assign it to A2. But anyway, so now what changes is over here. So this doesn't change. This is still gonna be 1. But over here now, what do we have? So this is alpha and this is 2. Okay, this is gonna be alpha. Sorry, this has to be written in terms of fn minus 2. So I will have a2 minus 1 comma minus 1 equal to alpha, and a2 minus 1 comma minus 2, and that is going to be equal to 2. Okay, yeah, that's pretty much it. Now let me make another solution. Let me call it G. This will be the inverse of A2, and we expect the solution from A2 to be more accurate than A1. Let me also plot alright, let's run it. We have too many grid points. Let me make it 10 to highlight the difference. Perhaps the exact solution we can put as a marker, and for the exact solution we can take maybe only 6 points. So because it's an exact solution, we know that the markers will be exactly at the correct point. So look, the second order solution is far more accurate than the first order solution. In fact, let me make it first order. So just to say that it's the boundary condition is of the first order. Okay, the second order boundary condition matches quite well. So what you can do is give a go of this technique that you learned, the ghost node. You can do it for any. You can open up a textbook and find out any equation that you have. You can try to solve it using this technique. And I've shown it for a linear equation, but you can extend all this calculation for non-linear as well. And you now know the tips and tricks to how to implement all of this in any language really. We're not dependent. All we have used is the inverse finding trick over here. And actually, in the next class before beginning, I'll discuss a bit about various other algorithms. So you don't really go about finding an inverse. These are direct methods, so to say, but we do it iteratively. I'll just make a small note on what techniques do exist and what is being used, because once you have large systems, finding an inverse of a sparse matrix is not that easy. Okay, so go ahead and try different problems from your textbook. You have analytical solutions as well. You can try to plot them to convince yourself everything works. Okay, so with this we end this. In the next class we'll see how to use some of the inbuilt libraries in Python to do all this thing in a very small, wrapped way. Okay, so we'll be using the solve bvp command, and I'll discuss about some solvers. So with this we conclude this lecture. I'll see you next time. Bye.